Welcome to CS229. This is going to be lecture 3. We're going to talk today about classification, which is, arguably one of the most fundamental tasks in machine learning, and one which started a lot of the progress that you see today. And so classification, if you recall, is going to be this problem where our label space comes from a bunch of discrete outcomes rather than continuous outcomes, which is what we saw last time. In regression, you could have prices. Here you may have, cat versus dog, you may have different words. They come from a discrete set. And that will change a couple of things inside our setup, right? So what we're going to do first is we're going to take something we already know from last time, and we're going to tweak it just a little bit. So we're going to see linear regression, which we saw last time, but now we're going to give it a probabilistic interpretation. And the hope from doing this is that you can see that, this method of going over the probabilistic stuff, just that piece of the modeling is changing. So hopefully, you're not seeing two things change at once. Once we get to the form of having a probabilistic model, and what it's going to do is basically model, as you'll hear, some errors, we're going to use those errors to talk about other forms of models that we could have, and in particular motivate the workhorse for what we're going to see now, which is logistic regression. And as I would say, as I mentioned last time, logistic regression is kind of the last layer of every model that you've probably interacted with. If it's text or code, in any ChatGPT, all the rest, that last layer is effectively what we would call a softmax or a logistic regression. And we'll talk a little bit about that. And then the last thing that we'll talk about today is also to give you a little bit of an idea about optimization methods. So last time we saw gradient descent and stochastic gradient descent. Those are the workhorse methods. That's what you're going to use throughout the course. But I'm going to show you just because it's kind of historically important and also kind of an interesting algorithm in its own right. I'm going to show you Newton's method just very, very briefly. Okay? Now, that flow, the thing that I want you to take away from all of this is this framework, which we're going to see again and again for the next couple weeks, which is this maximum likelihood method. And basically the idea here at a very high level is you set up a probabilistic model, a forward model of how you think the world behaves, and that determines what the parameters you're solving are. Okay? And we'll see this will be made concrete, but I want to make sure you hear this kind of high level piece. And then what that essence of this model, this maximum likelihood, that's the thing that's going to generalize across various different setups. It's going to generalize both from continuous to discrete to all kinds of interesting new models that we have, all the way into the modern AI models that we use today. And so this method is just something you should know. It's really foundational. It's kind of the bedrock. And we'll try and introduce it here as quickly as we can. First from linear regression, so it's nice and simple, and then bumping up to discrete stuff. Program clear enough? Awesome. Let's get to it. All right, so recall from last time, we were looking at least squares, and the point of this is that we didn't really have a full kind of justification for it. So we're now going to try and justify what we did in least squares, which you already hopefully know and feel very comfortable with. But we're going to try and put it in this new, more probabilistic modeling context, and that's going to be the lever that allows us to extend it to many new and potentially unfamiliar settings. So what we have here, if you recall, is we have a bunch of points xi. These are vectors that live in d+1. And recall the d+1 comes because we have this convention that they all have one component that has 1 in them everywhere, so that we can talk with a kind of nicer notation, just so we don't have to have what's called a bias or an offset in our notes. We also have for every point a corresponding label. This is because we're still in supervised land. In supervised learning, you have labels. And the labels here, because it's regression, come from a continuous space. Here, one of our favorite continuous space, just real numbers. Okay? Now the goal is, or if you recall, we're gonna find some theta, and that theta is gonna live in our d+1. It satisfies, we derived at the end of last lecture, that it satisfies this equation that I just highlighted here, which is theta is going to be the minimum over some set of errors. And we talked about these errors here here's the prediction. This is the hypothesis theta applied to the point xi. Mechanically, it is just this linear inner product. And then there's an error here. This is the error term, if you like. Which is how far off we are from the label, our hypothesis on x predicting the yi, and we pay for it in the square. And we talked about last time all the reasons we paid for it in the square. I won't go over them again. Mathematical convenience, and also some modeling. Today we're going to focus more on the modeling aspect of that and try and see kind of what consequence that has. What's another way to interpret this model here? Okay, good enough. All right, so what we're going to talk about is where did this model come from? And we're going to try and justify it in terms of something that's hopefully a little bit more simple. Even if you don't buy that it's any more simple, That doesn't really matter. It's another lens to view the problem that's going to allow us, as we said, to generalize. And this probabilistic interpretation is really critical in machine learning. It was kind of the core way we did a lot of things. And it's still, you can see it lurking underneath many of the models that we build today. Okay, so here it comes. If you haven't seen something like this before, it'll take a little bit of a second to think what's actually going on. If you have seen kind of stats models, it's basically a statistical model. So we're going to make an assumption, which is a little bit weird. Okay, we'll talk about why it's weird in a second. But what we're going to assume is that the data that we see is generated according to some process, and that we know something about that process. Or rather, we're willing to model that process in some way. So here we have our first example of the simplest process that we could imagine. We'll make this increasingly more complicated as we go throughout the course. So what is our process? What we imagine that the process that we generate this data from is that every data point, effectively, there exists a true theta that's out there in the world. We don't get to see theta, but it exists somewhere. And then when we see yi, remember we talked about that yi wasn't, perfectly accurate. Some noise term is introduced here, epsilon I. Okay. Now, epsilon I, we don't know perfectly. We don't get to observe it. It's some error that's in the system. And that epsilon I is going to capture kind of euphemistically noise. So what does noise mean? Well, it can mean lots of things. It could literally mean experiment noise. It could mean that there's some jitter in the equipment. When we measure it, there's some error because, the magnets are off or whatever it is inside. There's little errors that are in there in the background. It could also, and the way I prefer to think about it, it could also be what we're willing to model up to. Okay? That one, it's going to take a little bit of getting used to, but what it means is there's a bunch of errors that maybe we even know are in the measurements, but we don't want to model. We want to see how well our model can predict without having to go into that level of detail. So it's really an abstraction problem when we do modeling. And that's really important to keep in mind because one of the things that can really twist you in knots is you can look at a model and say, is it true? And the problem is the quote will be used in every statistics class you take, all models are wrong. Some models are useful. And so we're really talking about utility in terms of the abstraction, okay? But these are the kinds of things that we will typically think about as in the noise, on model effects, measurement errors, things like that, okay? So what properties are we going to assume about the noise? There are many that you could have of increasing complexity, but we'll start with one of the simplest, which underlies a lot of what we do in machine learning, okay? So let's talk about formally, okay? Now, as I say, the quote has to be there. Sorry, I should have waited half a slide. And this quote has to be, it's like I was walking in, by the way, through the coffee shop, whatever, in Y2E2, and I looked into a room and I saw the same quote. They had a nicer slide, if I'm going to be honest. It had like the picture of the guy and the whole thing. It was way better done. It wasn't just some little beamer thing at the bottom. They really put in some time. Good on them. It was a TA, if we're going to be honest. Any case, my point is that this is the canon of modeling. You want to know up to what are you modeling, and you're going to kind of box the errors. And you're making some assumption, always, in everything we do. And those assumptions are pretty interesting. Okay. All right, so what should we expect from epsilon I? Okay, so it's going to be a random variable. We're going to assume it's stochastic. That's going to allow us to do a bunch of analysis on it, okay? And in particular, what we're going to assume is epsilon I equals 0, okay? The expected value of epsilon I. So the mental model we have is that we're drawing these epsilons, right? We don't get to see them, but some source is drawing these epsilons and has some error in there, but the error is not systematically biased. Why is the error not systematically biased? Well, if it were, we would be in kind of a tough shape with our model, right? Because it would mean there was some offset that was hidden from us that we couldn't understand when we were doing the regression. So kind of this is one we're making almost out of necessity, right? We're saying, no, there exists a real theta I, and all of these epsilons, they're not biased in any way. Now, you can have biased errors. We'll come back to that later. But for right now, this is the unbiased assumption. Hopefully it makes sense. On average, there's nothing in the data set that we're generating that's kind of precluding us from finding that right theta. The second, which you may have encountered before as well, is that they are called IID, or independent and identically distributed. This is a very strong assumption overall, but it's a good modeling assumption. It's going to be one we're making for computational reasons, really. It's going to allow us to do a bunch of math in this lecture that allows us to simplify a bunch of our calculations. And again, it's a modeling assumption. It could be wrong. It could be that you have data from source A and data from source B, and their error profiles are totally different, right? When I collect and I pool that data, I get all the errors from source B have one variance and another have different variants, and I put them together. This model is going to ignore that, okay? Now, you could model that. We'll come back to how to do that later. But is it clear? It's a statement that this model is capturing it. All of the errors are uniform in some way, and they're independent and identically distributed. So what does that mean? Formally, what it means is when I take the expectation of any pair of them, if they're not equal, I can move the expectations inside. That is a factor. That is what we mean by independent. Okay? It's a formal, very strong version of independent. The second thing that we mean, this is just denoting it. Oh, so I see it's cut off. Is we think the variance, or the square term, is the next thing we're going to model. Now, you could model a lot of it, right? You could track your errors and track what are called every moment. You could map the second, the third, the fourth, the fifth, the sixth. You could put all the things in there, and maybe that would tell you something about the function. But all we're going to say is that we model just the first non-trivial piece. Okay? So we have two things. We have this 0. We have their independent. And we're going to model this variance. And this is kind of a measure. I'm going to show you some examples of this. This is kind of a measure of how noisy the data is, right? It's kind of the measure of the spread. And we'll talk about that, and I'll show you if you're not familiar with this in just a little bit. By show of hands, who has seen Gaussians before? Knows what IID Gaussians are? Awesome. You guys are going to have no problem with this. It's going to be amazing. Awesome. All right. So it turns out that this definition here is exactly going to lead to Gaussians. Okay. So you may ask, this is actually, Gaussians are a nice and beautiful thing that we use all the time because they have these nice properties. One of the things that they are characterized by is that they can be zero mean and just be described by their variance. You may say, what if I want to get a better model that's described by more orders? Turns out those don't exist. This is a uniquely defined. Gaussians are uniquely defined if you make this assumption. And so they show up everywhere in statistical analysis. Okay, so they're just kind of the workhorse. And they're a really good first kind of approximation. They're not something, just so we're clear, it's not something where you're like, oh, is the data really Gaussian? It's not a categorical kind of thing you're worried about. You want to know if the Gaussian model is good enough for whatever you care about. So if it turns out that the Gaussian model gives you a really, kind of terrible fit to your data, and you need to model the errors in a more precise way to get the accuracy you want, then Gaussian isn't right for you. But it's a sliding scale. It's relative to what you want to get out of it. And one interesting thing that's amazing is if you get enough data, law of large numbers and a bunch of other things, as long as it's bounded, CLTs and all that, if you know what they are, it kind of turns out that this is a pretty good model. So it's a great place to start. Okay? All right. All right, so let's see this. Actually, before I go on, any questions on the setup before I go to, please?
Is it because the error is y minus the...
Oh, wonderful. Yeah, great question. So what we're doing, so we haven't really talked at all about how it impacts y, but you're already one step ahead, which is phenomenal. You're basically saying that yi, if I think about yi's distribution, it's clearly going to be a function of this character here, which is the actual model underneath the thing, which if I had the right theta, I could compute, plus this thing here. And now I can look and see what the variance of the yi's are. This is a statement just about the random or stochastic part, which is just the epsilons. This statement makes sense even if there's a more complicated or crazier model here. It has nothing to do with the yi's. But from this, you're exactly right, and we're going to get there in a second. You're going to be able to determine the distributions of the yi's as well, conditioned on having theta, if that makes sense. And if it doesn't make sense, it'll make sense in a couple slides. Yeah, awesome. Great question. Please. Exactly right. Yes. It's exactly a variance here because the mean is 0. It's a wonderful question. Perfect. Awesome. Other questions? Fantastic. Okay, so what does a Gaussian look like? Let's see. Somehow this is getting cut off a little bit. All right, so I'm going to start here and then I'll go down. All right. So we're going to use this notation. I hope this notation is familiar to you. If it's not, don't worry about it. It's just notation. It doesn't really mean all that much. This means that Z is going to be a normal distribution with mean mu. That's going to be its center, right? So in the last slide, the mean was 0. That's the expected value is equal to 0. And in this case, the expected value is equal to mu of Z. Okay, that's all that's saying. And then it's one-dimensional. So its variance, there's no covariance, so just a variance, is sigma squared. Okay? That's the normal way you write it, and you'll sometimes say that it's mean mu, and you'll sometimes use the standard deviation, which is the unsquared error. This is just terminology. Nothing deep is going on here. It's just how we call this. Okay. This notation means distributed as. Z is distributed as that. We will use this for normals for this course, or for this class. Eventually we'll have more complicated distributions that we're going to start to piece together. Okay. All right. So what does the normal itself look like? Well, it has this awful form. Okay? And if you understand it, like, you can look it up. It's not something, you don't need to commit this to memory or get it like tattooed on your arm. It's not that important. It's hopefully something that's relatively simple to understand what the pieces are and what they're doing. Okay, so I'm going to walk through what the pieces are and what they're doing, and then we'll move on just to remind you. So this is a probability function. Okay, so this is a probability distribution of z. We want to normalize it in some way, and so it's going to have a normalizing constant here. Where does that constant come from? Well, we're going to integrate out over the rest of the function. So this is probably the least important part of the entire formula. If you forget this, you can do almost all the machine learning, and you'll see in a very precise way, constants will fall away when we start to minimize it and put it into things. So it's really not that important. But it's nice to know so that you can compute it exactly. The action goes on under this exponential. We're going to see that a lot of machine learning, at least for machine learning from like the early 2000s, especially, they love putting things under exponentials. That made them feel good, okay? So they have the same model, they put it under exponentiation. They went from like, doing something ad hoc to doing something principled, as they would say. Never really understood, but all good, okay? There's a reason for that, which we'll talk about next lecture, which are called GLMs, generalized linear models. I'm being a little bit facetious, just to say that exponential has a nice form to it that we use, but don't get too uptight about it. The action is in here. This says, and this is like hinting about why least squares will come in, my distance to the mean squared is going to enter for my distribution, how likely it's going to be, roughly. We'll make likelihoods clear in a second. And I'm going to divide by 2 over sigma squared. Why? Well, that's that 1/2. It's for normalization and convenience, right? We're obviously going to take a derivative at some point, and that 2 is going to cancel out, okay? Otherwise, we wouldn't write it. It's a little bit of cooking show kind of math. And sigma squared, that is the variance that we talked about before. And so it scales in units of the variance. So intuitively, if you think about it, if you get 1 unit away, right, of sigma away, you go down by a certain amount, so another amount, and you pay kind of quadratically. And so you get this beautiful shape here, okay? And so these are the usual things that you show that says, oh, if you get 3 sigmas away from the mean, 99.7% of the mass is concentrated in that region. So it's a very tightly concentrated thing. So if sigma, just to be very clear, is like 0, close to 0, then it's very, very sharply peaked. And if 0 is very large, relatively speaking, it's very flat distribution, okay? So Gaussian, those are both Gaussians. They just have to deal with how wide is this area here. Hence why we use it. Okay, hopefully this is review. If it's not, please check it out. Ask questions too. I'm super happy to talk about it. Please.
Can we model asymmetric or multi-model distributions with Gaussian maybe that may like overlap?
Wonderful question. The question is, can you model distributions that are asymmetric? Because this distribution that we just talked about is clearly symmetric, meaning the distance between mu here is symmetric in both directions. So you fall off just as fast this way as this way. So the observation is symmetric. Can you model things that are asymmetric with a Gaussian? Not that piece of it. The second is, can you model multimodal, which traditionally means that it has multiple bumps. We will see in a later lecture, I think I'm going to get the lecture numbers wrong because we switched them this year. It's usually around lecture 11, I want to say, or 9. We're going to see a model called the mixture of Gaussians, where indeed you can use many Gaussians as building blocks to kind of build up multiple bumps. But today we're just going to worry about single Gaussian. Perfect. Great question. So yeah, so you're already identifying, just to point out, you're already identifying some things that are strange about this distribution, right? We talked about the errors. The fact that it's symmetric means it's not, for example, aiming too high or too low in the prices, right? There's not a systematic bias in one direction. That would give you something that was asymmetric in the errors, right? We're just going to assume we don't know that information or we're not willing to model it. The other bumps is a statement that there is kind of one kind of noise source, but you could easily imagine that there's multiple noise sources. Remember my example from earlier? We had an A and a B station. Maybe they have very different variances, and so their distribution's kind of a mix of 2. We'll see those examples later. But for now, just one humble Gaussian. Okay, cool. So this is related to the question that came up earlier about Y's and all the rest. So recall our model, and let's start to see some fancy notation. So hopefully this is something that you're familiar with. If not, don't worry too much about it. Here's how it works. So we're going to have this notation where we have this mathematical equation which says our yi's are a function where mechanically we plug in theta. We don't know theta, but this is like, a theta that's hidden from us. If we did know theta, we could plug it in. We plug it in, we take this dot product, then we add in the error that's randomly distributed, and that gives us the yi. Okay? This notation says exactly what I just said. Okay? It's more compact. It says the mean is exactly this. These two terms are the same. I'll let all that red ink drain off. It's a little slow, but all good. And then this sigma squared is this sigma squared. Okay. Now, why is that? It was alluded to by the question that came up earlier. Why is the variance of yi the same as the variance of the original epsilon that's in there? And the reason was exactly stated. Here, if I look at the distribution, if I were to take theta xi and subtract it off of yi, and then take its expected value, that would exactly get me back to sigma squared. Okay. Said another more formal way, what we're saying is that yi, conditioned on seeing the xi's and thetas are a parameter, are distributed as a normal with this mean and this variance. This fact that you can just copy is not automatic. Like, for example, if we multiplied epsilon by some scalar value, we would have to track that when we went to this model, right? So it just happens to be that these things are all linear here. That's why it works out and it's the same sigma squared, right? If you multiplied a number by 10, you would expect the variance to go up, right? Not a strange statement. Okay, cool. All right, now that gets us down to here. Now, all we're doing is we're plugging into that horrible formula we saw before. We're plugging in all the terms. The mu is the old formula we saw before. The yi's are the same. The squared is the same, 2 sigma squared. And the normalization doesn't really change here. Okay? Because the sigmas were really responsible for normalization, right? Sigma's the mean didn't appear in the normalization, only the variance. Because the mean is just shifting it around, right? That's not going to change how much area is under the curve, so you wouldn't expect the mean to change the normalization, but making it kind of wider or narrower, you would expect that to change the normalization. Indeed it does. Okay, hopefully this formula is making intuitive sense. The details of it, if the details aren't quite there where you couldn't generate the formula, play with it. It will eventually become a little bit more natural. But all I care about really is that you kind of understand how it's put together. What are the key components? There's a distance squared, there's a variance that normalizes the units that are there, and then I hope that this notation doesn't terrify you. If you haven't seen this notation before, that's one that I would pay attention to because we will use it quite freely. This kind of condition and parameter notation, I use it, kind of without thinking. If I say something that doesn't make sense, or you don't know the notation, please feel free to ask. It's not that deep. It's just, you can always write it out. It's just mysterious and you get used to these shorthands. So I wanted to highlight it. All right. Now, this basically says what we just went through. We condition on xi. Conditioning here means that we assume that we see it, right? We have access to xi when we're making the distribution. So the distribution is fixed once we have the xi. This makes sense, right? Well, if you think about it, every xi is a different data point, but the errors for each one are going to be stochastic. So they're setting the mean. They set the average of where we think is going on. And in contrast, this is a bit of terminology that you'll see. Theta parameterizes. You're not actually conditioning on theta. It's not an event in the space. I don't want to be too precise about it. It's not something you condition on. Theta is just a parameter. So there's many different distributions out there. Each one parameterized by theta. And what we're going to do in a second is we're going to basically pick over all the distributions that could have generated this data set, which one is most likely. And that's going to be the principle of maximum likelihood. That's it. It's honestly it. Okay. So this just says we're going to search over the thetas. We don't really search over the data yet. Okay. We don't search over xi's. Those are given to us. That's input to the problem. Okay. Yeah, and you'll see me use the bar versus semicolon notation. Here, the semicolon indicates that there are parameters on this side, and the bar here is indicating this conditioning. Please.
If you had like a theta and a gamma, like multiple parameters, would that just be a theta comma?
Exactly right. So the question is what if you have multiple parameters here, and what happens is you have theta, and then you would have, exactly as you said, to keep your example, you have a gamma, you have an alpha, and so on. They would just be concatenated there, or sometimes put into a little tuple of values, or what you'll often see, because I'm extremely lazy as a human, I will just write something like, oh, there's like phi, and you remember phi bar has all the parameters, and it's up to you to go source it, and maybe I screwed it up. Yeah, great question. Other questions? Awesome. All right. Okay, so now we can talk. I've been saying this intuitively as I've gone through it. What is a likelihood? So we've been talking about what's likely or not likely, and that actually is, underneath that is lurking a somewhat formal phrase, okay? So the intuition is, as I said to you, among the many distributions that are out there that have your data. So the mental model is, you show me, remember, a bunch of xi's and a bunch of yi's, okay? Those are what showed up. And now, what I'm going to try and do is, for each setting of theta, I can tell you how likely that data point is under the model. Okay, so sorry for the larger box. This is the box I care about, which I'm now covering up and making impossible to read, which is perfect. Sorry. So this one here is saying for each data point, it says, given xi and a yi pair, I can tell you how probabilistically likely it is, okay? And that's basically just evaluating that function p that we had before. It was higher on things that were more likely, lower on things that are less likely. Okay, let's not make a big deal out of it. And always non-negative, okay? Now, why do I take this product over all the data sets? What am I using there? Well, there's only one assumption written on the slide, so it's fair to guess it's this one. How is that happening? Well, what's happening here is you could imagine I have the probability of all the x's and all the y's simultaneously. That would be some big, really gigantic function, right? That had conditioned on all the x's and all the y's simultaneously. And instead, what IID is allowing me to do is say that function can be represented as a product. Okay? And that's what this notation means, by the way. It says all the y's and all the x's. And this cute little notation belies the fact that that would be huge. It would be a n times d dimensional thing that I was looking at. That would be really, really big. This is a massive simplification that IID gives me. Because they're independent, I can basically turn them into a product. Okay? That's what independence means. It really is a factorization. It means that it's a product. It's not a mysterious property of it. It is literally, effectively the definition. Okay, cool. All right, now, this score, which I just substituted in, I didn't do anything fancy, I just took P and substituted in the last slide, right? So this score now, for every theta, there's a score which I can compute with this nasty formula. You could write it in, whatever you want. Claude Code could write it for you, PyTorch could write it for you, NumPy could write it for you, whatever, okay? You could write it in raw Python. Whatever you want, you can write this thing and it's going to give you a score. And the idea is that if theta is a better model of the world, it should say that the data is more likely. So if I were to compare two thetas, theta 1 and theta 2, and one gives me, score x and the other one gives me score y, and x is bigger than y, I'm probably more likely to pick the more likely one. It fits the data better. Intuitive enough? Clear enough? Please ask a question if not. Okay. All right. Now, it turns out, remember I told you I didn't care about normalization constants. In general, that's true. But here, why this is so nice is because these things are all, greater than 0. I can take logs. We love logarithms. And the reason we love logs is they're going to turn this nasty product, which is, numerically unstable and has a bunch of problems, into some kind of nice closed form looking thing. And we're going to have logs of all the normalization contexts minus, because there's a minus here, all these characters there. And that's going to be little l, or script L, is going to be the log likelihood. And you'll hear me use the log likelihood all the time. It's just the log of the original function. So far, so good? Now, we wanted to maximize this guy internally, right? That's how we were thinking about it. We want to pick the theta that had the highest score. Here, because after we've taken logs and we have negatives, we're going to see that we may want to change that, okay? All right, so let's get that. All right, now, as I mentioned, this is just some arithmetic simplification. We pulled out the term. This term was constant, so we didn't have to deal with it. We had this nice, form here. And lo and behold, if you remember the notation, if you're like a real notation aficionado from last week, then you see that this j theta is exactly the loss term that we had in least squares last week, okay? So this is just this character right here, okay? And this 1/2. This made j. Okay? That's just notation. If you don't remember that, don't worry. But that was the least squares loss. So basically what we've done is we've gone from some probabilistic model to where a constant, which no theta changes, right? Because we were not putting, theta does not contain sigma. That was fixed. We now have this. And so what we've justified is that least squares is basically this model where we have fixed variance, but we have errors that are IID. And that's it. Mean 0. Yeah, please.
I was just wondering, why is the probability guaranteed to be positive?
Oh, great question. So in this particular case it is. In general, it's not actually guaranteed to be positive, and that causes a whole bunch of pain when that's the case. Here, because this thing, the exponential, has that nice property that this is never exactly 0, we can pass through the logs here. If, for example, you have a distribution where the question was, if p is 0, what happens? Clearly it's non-negative, right? Because it could be 0 places. If you have things that look like discrete distributions, then you have to be careful about what your domain is. You can still do this log trick, so it will still show up, but it's something you should pay attention to. If you start taking logs of zeros, all bets are off. Yeah. But so this transformation happens enough that we're going to use it. And in fact, as we'll see later, most of the distributions we have effectively make sure that this happens. And you should check that as you go, right? And we will check it whenever I use the transformation. But it's a great question. Yeah. Cool. Awesome. All right. So this is just restating what I was saying before. We've shown that finding theta is, we wanted to maximize L theta. So we had this model, and we motivated that on entirely intuitive grounds. Among all the distributions that were out there, we wanted the one that was most likely, that it kind of explained our data the best, right? Again, all the data that were out there, we measured them against the data. That was L theta. We showed that that was the same as this, maximizing this character, right? And then this thing, we recognize as the least squares loss, but it shows up under a minus sign. And so I'm ruining the punchline. That's why we were minimizing it. Last time we were minimizing the errors. This time we were maximizing likelihood, and minimizing this fell out. Constant minus that. If you think about taking a derivative with respect to theta, this term would go away. However you'd want to think about it, it's clear that that is equivalent. That's the part that you have control over. Okay? Now, you say, at one level, you look at this and you say, well, this seems like a bunch of needless symbol pushing. Why did you waste my time with this? Fair point. But the reason is because this principle of maximum likelihood is actually more general than least squares. So one of the things that you're going to have in machine learning is you come to a new problem, you want to model it, and it turns out that it's a lot easier to think about forward models. Now, that statement, just so we're clear, that modeling statement is with a huge asterisk on it. I'm saying in practice, or in academics, or all the rest, we found it easier to think in terms of forward models many times. And so this is a recipe that works. Okay? It's not saying something like, you can only think this way. Many other ways to think. But this is why it's so popular. And then once we have a forward model, we're going to see over this lecture and the next that you basically can turn a crank and always get out some optimization procedure. And that's going to allow us to solve a range of different things that in the machine learning literature, if you were to go back in time and look at them, they look quite distinct, but actually they're all instances of one kind of generalized framework. And so that's quite useful for you to know in case you encounter, your particular kinds of errors that you have, discrete errors, count errors, all the rest. And we'll see some of those in the next lecture. But for now, is it clear that why this maximum likelihood I claim reduces to this least squares thing that we saw last time? So we have justified that model. Okay? All right. Good enough. All right. Okay, so the summary of least squares, we introduced the maximum likelihood framework, which is super powerful. We're going to use it in the rest of this lecture and in the next lecture. We showed that least squares was actually a version of this maximum likelihood kind of event. And we learned some notation still that we're still loading up on probabilistic notation, the most important of which was the conditional and the distributed notation. What does it mean to be distributed as a normal? And what does it mean to condition on things? What are parameters? Those are the notational elements that were important from this section. Any questions here before I move on to the next topic? Please. Right.
Do we need to have an estimate, or is it a free variable?
Awesome question. Yeah, awesome question. So the question was, where does that sigma squared, where does it actually come from? Do we have an estimate of it? So on one hand, the simplest version of the model is you kind of just assume it, or kind of look at the data and fit it, outside of the modeling procedure. That's kind of the practitioner's answer to it. The other is you can create a maximum likelihood where the variance is also unknown and you're fitting it as well. And so that's a more sophisticated example where you would actually put that in. But this comes down to the modeling question. What are you actually fitting from the data, and what are you assuming as what we'll call a kind of a prior distribution? What do you assume you know about the data? I would say if your model is such that small changes in a parameter like that change your conclusions, you should be very nervous, okay? And so one of the things is if you see, there's a lot of times when you'll do what people call hyperparameter tuning, well, they'll fit a range of those different models to their data. If they lead to totally different conclusions, that should make you uncomfortable. It really should make you uncomfortable because it means that there's something else going on that you're not modeling, and it's important, okay? If you change a parameter that you don't think should matter and nothing happens, that's a really good sign, right? Like, so if you sweep the variance and you're like, as long as I'm within 2 orders of magnitude of, variance 1, I get kind of the same answer, you feel very comfortable as a statistician, okay? Or as a machine learner. Okay. Great questions. Others? Awesome. Let's keep at it. Okay, so now onto the topic of classification. So classification is, we're going to look at binary classification. We'll eventually look at multi-class classification. In binary classification, it's a simplified setting where we have our friends xi's, right, that are there. We also now have yi's, and those yi's are going to be modeled as just 0, 1. Okay? So you can imagine as like, cat or not cat. I don't know. Whatever you want. Okay? Whatever makes you happy. It's just a binary thing that says, is it yes or no? Okay? That's what our yi's are. Right? So now the first question you should probably ask is, why do I need to do anything different? I'm going to take my data, my x's and my y's. Why don't I just run them through the least squares thing that you did before? That seems like it should give me some kind of answer. I can fit the x's and the y's and I sit there. So what does that kind of look like? Let's draw a picture and kind of see what the traditional pitfall is. So we have data and our data is like somehow arranged here. I'm going to try and get some blue ones. So that's way too big. See if I can make it smaller. Okay, too small. Perfect. All right, so we have some blue ones. These are going to be, our negatives. These are our zeros. And then we go along, and then all of a sudden we get some positives. I'm going to make those the reds, and they're up here. Okay, this is 1. Okay, this is how it looks. Okay, so far so good. So if you look at this intuitively, what's the decision surface that you want? You somehow want to get a line that kind of fits in here, right? That kind of cleanly separates them over time and kind of figures out where they are. The problem you have if you start to fit something that looks like least squares is, well, in classification, if we just care about separating the zeros from the ones, right? We just care about that split. We don't care if there's some, blue that's way, way, way over here, right? Over here, over here, over there. But if we're doing least squares, all of a sudden, we start getting hyperplanes, I use green, that instead of being kind of like nice, well-behaved hyperplanes, they start stretching out more and more and more. Okay? So this is just intuitive. You can run this exactly as I've described it, but hopefully it makes sense. What happens is as you start to get y's the x's that are going farther and farther away, instead of just finding the exact spot that splits them, I'm somehow trying to do something else. And the something else is I'm trying to kind of find their center of mass, right? And that seems inappropriate when I'm just trying to find what we'll call like a classification decision surface. Okay? All right. Questions about that? Clear enough? All right. Okay, now, all that said, if you have actual data and you try this out, these squares will work more often than you think. Okay, so all that being said about it not being a great formal model and these issues about what happens when you get these tail data points and all the rest, they're all true. They do happen. I'm not telling you nonsense. But intuitively, when you get high-dimensional data is pretty weird. And what I mean by pretty weird is it has this strange properties like your closest point and your farthest point are often the same distance. Very strange things happen in high dimensions, which are different than you may picture. And so when you have real data, sometimes you just run a model that's pretty bad back to it, but it does a good enough job. And that can definitely happen, okay? So modeling is not a formally correct or incorrect thing. It's always a matter of degree. All right. But for classification, it's kind of a nice type thing. Okay, so you should use a classification function so that your predictions, someone doesn't ask you yes or no and you predict 7. That seems crazy, okay? So you'd have to have some code over there that says if my function says 7, I round it to 1. If it says -40, I say 0, okay? You'd have to have code on the outside to do that, which also makes it a little bit more of a hassle. Okay, so let's look at the most common classification function, and this is the one that is the workhorse of the stuff that we do today. We're going to have these things that we'll call a link function. So our hypothesis is still going to be linear, right? So there's still this linear element to it, but we're going to add in a nonlinear element g. And g is going to be called a link function. Okay, so it's going to have some shape. So what would you want g to have? Well, you'd probably want it to be monotone. It'd be super weird if it wasn't monotone increasing, right? You give it a higher score and it just randomly gives you a value. So g shouldn't be stochastic. It shouldn't go from 1.1 to 1.2 and then go from returning 1 to false. It shouldn't just go. So it'll probably be smooth and monotone were things that we would want. Right? So let's look at it. So there are many that you can pick, and there are actually entire stats books that you can read. I even own some of them that tell you various different functions. But here's one that's very, very popular. Okay? Right? And this very popular function has this nice, beautiful sigmoidal shape where it starts down at 0 and it goes up. Now you may look at this and say why don't I just use a threshold? Why don't I just say, go to here and that's my function, the step function. The reason we don't use that function is, well, it's non-differentiable. And so it's not convenient mathematically. Now, differentiable isn't a hard boundary for us. Actually, in a lot of neural nets, not so much as anymore, but a lot of neural nets, say 5 years ago, they used other functions like ReLUs and things that kind of look like that, which are not differentiable, but kind of hinge losses. There are other losses that you could use. But here we're just going to focus on this nice one because it has this beautiful scaling between 0 and 1. And it's going to show up and give us the most popular model, which is logistic regression. Okay. All right. Okay. All right, so how do we interpret this thing? So basically we interpret it as being in the class is its height. So h of theta is going to be this kind of probabilistic thing. And 1 minus h of theta is going to be the probability it's not in the class. Now this is already interesting. Before we were just predicting a scalar. Now I'm telling you that when we predict something, we're going to think about it being the probability that's in the class. So if it's very, very close to 1, right, intuitively, we think it's very likely to be in the class. We will not return exactly 1. We may return 0.999. But we're going to return and say that that's very close to 1. And then there's 1 minus, because it's binary, that it's in the other class. Okay? And the reason I highlight this notation is later when we do multi-class, this will again come up, right? We'll bake the classes off of each other. Any questions about how this works and what the type is? Okay, so all that I expect that you have thought so far is, okay, I have a new h theta, I have this new class of functions. They look relatively simple. They look like the linear functions that I used to have, from a couple minutes ago, except for now I've run them through this g function that's going to smooth out their values. So if theta dot x is going to be some huge value like 100, well, that's going to be way, way over here, and it's going to be very, very close to 1. Okay? That's the idea. You'll sometimes hear people call these logits, but that's a separate issue. Okay, if you know what a logit is. Okay, cool. All right, so that probabilistic interpretation is going to give us directly a model. Okay, so back to what we were describing before, we are going to go back and use our old friend, maximum likelihood, and we're going to try and, old friend from 15 minutes ago, so, maybe it's whatever. I'm not going to make a terrible joke there. Anyway, so back to this. You're going to go to the product. Why are we going to a product? We're again assuming some independence, okay? So we're going to have this nice product that's going on and what's happening. And then we're going to substitute our form in. Now, this is just notation. This is just if-then, written in a clever, statsy, machine learning way. It says either yi is 0, okay? And if it's 0, then which term is active? This term. Or yi is 1, and this term. So this is yi equal 1, y equal 1. This is y equals 0, okay? It's just putting the two terms there. And when they're off, they return 1. Okay, so just convince yourself that this function does what you think it does. If you plug in y is equal to 1, you get the term that you want, and it doesn't go to 0. If you plug in the other one, you get the other one. Okay? Hypothesis 1 minus the hypothesis. Okay? So far, so good? All right. Now, back to the earlier thing, we take logs. So you've already seen this movie, you kind of know how it goes, and we get this fun form here. I'm not going to beat it to death. It is yi, 1 minus yi. They have different things inside the logs. All we're doing is trying to walk back exactly the same framework that we did before, and this is going to get us to another one of those functions, which is a gigantic sum instead of a product. It's nice, numerically stable, all that other good stuff that happens from it, over our data points. Okay? How are we going to solve this thing? Any guesses? Differentiate, compute some gradients, let it run for a while. Okay. Now this one we can tell when it's finished, which is not going to be true later in the course. But this one we can actually solve. Okay. All right. So how do we solve it? We maximize. We already saw how to do this. You just compute the derivative, run SGD, and you're done with it. Okay. So that one, I just want to point out, was super quick to explain once we had gone through the basics of the story. We have a model. We know how to take the model and turn it from logs into a nice additive cost function. Once it's an additive cost function, we know how to run SGD on it, and boom, we can go and solve it. We can use gradient descent, stochastic gradient descent, whatever we want. This recipe is part of the reason maximum likelihood is so nice. We try to figure out how likely our data set is in the probability space. Then we go to the log space. That's a nice monotone mapping, which is great for us, right? Preserves that. And then, boom, we're off to being able to solve this in a big additive sum. It's additive, so now we know how to use SGD because mini batching and all the things we talked about last time. So it just snaps together. You were going to say.
Just being like a little pedantic, so just curious, would this be like gradient ascent because we're maximizing?
Oh yeah, great question. Yeah. So the question was, would this be gradient descent because you're maximizing 100%? You would change the sign from minus to plus here. We will actually put it in a form where it's gradient descent when we write it, and so I apologize if I said something that was confusing. But wonderful call out. I appreciate it. Other questions? Oh, you guys are great. Okay, but the thing that I want to show you from this is just so you see, this is an extremely powerful model. You like actually have used this model in your life, whether you want to or not. It's like underpins almost everything. And it's super simple once you understand those principles of how you put it together. You model it with maximum likelihood, you take it into a nice convenient form for computation, you solve it with gradient descent. This is the recipe for maximum likelihood that's been so powerful over the years. Okay, now, I don't know if I'm going to go through this very quickly. You don't need to know this, but there's something that I do want to show you. And there's a little bit of math on this thing, so if you have the slide, you can go through it. But let me highlight for you among here what's interesting. The interesting thing is, and this was the great thing before, so I sneakily switched the sign from minus to positive exactly to deal with a ascent issue. This is the mini batching that we were talking about before. But the remarkable thing is this. So when we wrote the original form down here, this is a strange looking object. But what's weird is you can still get to something that has this nice familiar form where you measure the error and multiply by xj. That's pretty nice. And it turns out this is a general rule. We're going to see it more later in the course, so I want to highlight it now. Later in the course, like Wednesday, not like 6 months from now. This form, this error and correct form, is very, very common. And it's nice that these models have it. So all the nastiness is put into infer on the point, look at the data point difference, and then do an update. It's quite remarkable. Okay? Not obvious. Derived here, okay? With a bunch of just algebra. Just algebra to go from here to here. Don't worry too much about it. You can do it offline. Okay? Not gonna torture with it at the moment. Okay. So what did we learn? We use the principle of maximum likelihood in a probabilistic model to extend this work to classification. We developed logistic regression from this principle. It's extremely widely used today. This is a model that, like, as I said, you've probably used or used a product that has logistic regression or what's called softmax inside of it. Important for me is you've seen this principle. Next lecture, what we're going to do is we're going to take that same principle and we're going to run it on more complicated distributions. And again, this part of the crank is going to be very useful for us. Don't worry, you'll see it again. Model the probability distribution, take kind of logs to put it in the nice form. We'll talk about what the nice form is, and then we'll run gradient descent. And then you can run all that back-end magic that we care about and love. This is the familiar pattern, and hopefully it's intuitive that it gets into this misprediction form. I skipped over that a little bit, but that was what I was talking about in the slide, that you get this y minus h theta thing going on. It will turn out that almost all the models we consider in this first couple part of the course have that form, and hopefully that's intuitive. There's nothing mysterious going on in gradient descent, okay? It's just a first order approximation that says, I take x, I predict it, I see where my error is, that's the information I have. And then I take a step in a direction, and usually that direction is in the direction of the data. Boom, done. Okay? All right. Okay, so with our last little bit, I want to show you one little bit of optimization, which is Newton's method. And here, it's just a different optimization. We're not going to use it that much in the course. For logistic regression, though, I should say, so something that's interesting, there was a while in machine learning a long time ago where logistic regression was like absolutely the vanilla workhorse. This was before PyTorch and all the rest, TensorFlow, all those other tools, JAX. What people would do is they would take logistic regression and they would add in huge numbers of features. So they'd have very, very high features. And you could take those X's that we talked about, instead of putting them in low dimensions where you'd have like, house prices and all these other things, they would take random hashes of them. They would just make them, they would explode them. There's a beautiful paper written by a dear friend about what are called random features, which are unbelievable kind of we'll find out what kernels are later, but these unbelievable infinite dimensional feature spaces. So it's an extremely powerful model. You can put a lot into there. Solving those models, especially in statistics, you can, because it's convex underneath the covers, we won't prove that, but you can find the right theta. Now remember when we talked about before, I said, if you change, when we were discussing about the sigma squared, talked about if you changed a parameter and then all of a sudden the model changed, you should be very uncomfortable with the model. And I will just tell you as a historical note, machine learning people were very uncomfortable when they would run a procedure and get one theta, then they'd run another procedure and get another theta. It turns out that machine learning people realize we don't really care about theta as the object. What we care about is h of theta, the predictions we make with it. Okay? So I'm going to show you this because it is historically quite important, but what we care about now when we talk about stability is more on the prediction space than on what we would call sometimes the certificate or the parameter space. Okay. All right, so in Newton's method, let's discuss it. It's a simple method if you haven't seen it before. By show of hands, who knows Newton's method? Okay, pretty good. All right, so we're given here an f. We want to find the 0. We typically apply this to likelihood functions. We take the gradient of theta, right? So we want to find a stationary point, right? We want to find some place where the gradient is equal to 0. So we use it, on that piece, but we'll talk about it in full generality. Okay. So how does it work? It's an extremely simple method, which is pretty nice. All right, so let's say we have our function here. We have some function that we want to, try and find the 0 of. So here's where the 0 is. We start with an initial guess. It's iterative like all the methods we've drawn. So I'll call that, theta 0. Okay? And this point here will be, f of theta 0. Okay? All right, so far so good. Now, what we compute is the gradient again. This gradient character. Okay, and our method, the idea is that we want to find the 0, and what we're going to do is we're going to use this local linear model, this line here. So what is the slope of this line? Well, the slope of the line here is going to be the gradient. So this function here, which I'll call t of theta, right? So as I move back and forth on theta, I move up and down this line. Well, what's the equation for that line? Well, it's the Taylor's approximation, right? So it is f of theta 0, because that's this point here, plus, and then I'll do something like the gradient of f of theta 0 times theta minus theta 0. Okay? This is the Taylor's approximation. And then what I want to do is I want to set this so that t of theta is equal to 0. So I want to move up and down this line. And I want to get its guess of 0. Okay? I don't know, I can't figure out where f is, I only have this local information. This is my best local guess. Okay? Now, this is different than stochastic gradient descent, because in stochastic gradient descent, I would just look at the gradient, look at the direction, and take a small step here. This is telling me exactly how far to go. Okay? So it doesn't have a step size, which is quite a nice property of it. One of the reasons people like it so much. Also converges fast when it converges. So when we have this equation here, t theta, how does it work? Well, let's solve this. This is basically going to say that I'm going to take f of theta 0, I'm going to divide it by, I'm going to say here, let's imagine this is a scalar for the moment, just to make my life easier. I'll come back to what we would do otherwise. Minus plus equals theta minus theta 0. And indeed, I get here that this is going to be theta, out of things, theta 0 minus f of theta 0 over f prime of theta 0. Okay? That's going to be equal my theta next. I'll call this, theta t or something. Okay? So the guess is just, I go down here, I walk by the distance that makes this line intersect 0, and I repeat. Okay. Now the good thing about Newton's method, just as an aside, okay, so I set it equal to 0. What do I do if this is higher dimensional? Anyone remember? So if it's a scalar, I can go and do this division here. What really matters? What happened? Oh, please.
You did convert the...
Awesome. Yeah, so one idea would be if this method were, if f were of the right type, for example, it was a gradient, and a gradient has a type of going from, say, fd to fd, then the gradient of the gradient is the Hessian, right? That Hessian is square. Hopefully I can invert it and find the place where it's equal to 0. We'll write that down in 1 second. But more intuitively, basically what this says, and this is a question, it says if I have this vector, I basically have a vector times a dot product here, and that dot product has to be equal to f0, has to equal to minus f0. So among all, if I imagine a higher dimensional surface, I have to find among all the points that are there, and there could be many, right, because the null space is large. Are these terms familiar to you? By show of hands, who knows what I mean when I say null space? All right, good, awesome. Then I just have to find something there among all of those that gets there. And the answer is that I don't just use the inverse, I use the pseudo-inverse, because it may not be actually perfectly invertible. And the pseudo-inverse in particular, it's called the Penrose pseudo-inverse, does it exactly. It handles all of these cases directly. If you remember the little dagger, that's what's going on under the covers. Overdetermined, underdetermined. If it's overdetermined, what do you do? Any guesses? You have too many equations. So here it's underdetermined if I have kind of a d-dimensional vector and only one equation in the parameters. What happens if it's overdetermined? I heard it. You use least squares. Okay, so it uses the same algorithm we had before. It basically does a least square solve to try and find out what's the best direction underneath the covers. Okay. All right. So hopefully that's familiar and intuitive. If it's not, please ask questions. This was also, exactly as was talked about. When we have vector valued things, we'll use the Hessian, okay, which is described here. It's just the matrix of partial derivatives of the loss. And this algorithm, when it converges, and it has a pretty good convergence guarantees, it gets a good local convergence guarantees, it's extremely efficient. Okay, in a optimization sense, it gives you many digits of precision every time it runs. Each one of those steps is actually zeroing in on it quite a bit. Okay, all right. So why do we use SGD? So it turns out that this is the main trick. So SGD has OD compute per step, right? Mini batch is B times D, right? This is the dimension that's underneath the covers. And it may take SGD many, many steps to do there because it's a really bad estimate, right? From my last time. Remember, it's just like takes one term, guesses which direction to go, and takes a step in that direction. Mini batch is a little bit better. It takes a small collection of directions, executes and goes. Gradient descent is a little bit better. It actually computes the gradient for what it's worth. It really computes the honest-to-God gradient, but it has to see all of the data points. In a lot of machine learning, N is absolutely, absolutely massive. And so is D, okay? So like, for example, you want to train on every word on the internet, and you want to run a 10 billion or 100 billion or 1 trillion parameter model. Well, that's a really big number, right? It's like a quadrillion steps. You're not going to do that. That's too many flops to make one estimate. Newton is much worse in this regard. It's n times d squared plus d cubed. The d cube's coming from the inversions and other things we were talking about. Here's where we're applying it to the loss. You will do very few steps. What I would say, it's very statistically or optimization-wise, it's efficient. If you measured by steps, this annihilates the ones from before. But each one of those steps is extremely, extremely expensive. So as a result, this is just another way of saying mini-match SGD is a workhorse of ML, and I believe you're going to have a homework where you compare them, so I just wanted to make sure that you had actually seen the various different methods. Please.
Method used anywhere in that case, since it's so expensive, is it actually used for any? Yeah,
great question. So the question is Newton's method used anywhere? It's used all over the place in classical statistics. So for example, if you're going to train a model in a stats package, a SciPy, something like this, and you only have a couple of 100 features or something, or 20 features that you're trying to regress out, which to be fair, 20 years ago was the most common use case in stats, then you would use Newton or a variant called LBFGS, which is a limited memory kind of second order thing. You would use those everywhere because you really cared about the parameters. The reason that I include this is to give that contrast because a lot of people, maybe not as much now, but a lot of people come in with a kind of a background of stats and they're like, oh, I'll just solve these models with these great optimization techniques. And those optimization techniques indeed are great, but they require different scaling. And really what this is an excuse to kind of beat this again and again, that really we're interested in these regimes in machine learning where N, the number of data points, is huge, and D, the number of dimensions are huge, and that's a very weird space. And so you end up with relatively crazy things and the problems that we care about. But if you ask a social scientist, they would never in a million years use SGD. It'd be too noisy, too hard to tune. Newton's method doesn't have step sizes. Why not just press the button and it works? It runs before I even think about it. So it does get used quite a bit more over on those kinds of problems. Wonderful question. Other questions? Please.
I think Newton can be cheaper to compute if you have some structure like the Gaussian matrix sparse or something like that.
Yeah.
Are there any cases that you have huge data set with that kind of characteristics?
Yeah. I feel like I paid you to say this, but okay. So anyway, so the question was, are there any cases where you have some structured in H? And it's I don't know, maybe I had one student who now works at Meta, was his whole thesis was about when you could have structured matrices and Hessians that allow you to do something that's smarter. It turns out that you don't have to compute the full Hessian. This is not relevant for the course, so please don't listen. But I'm going to answer your question because I like it. The thing is, it turns out that you don't have to compute the full Hessian, but you have to compute Hessian vector dot products, and those can be cheaper. If you know the Hessian has some form, or you're willing to assume it has some form, then you do something in it. It's not really Newton's method any longer, but you have some second order information. That actually is used in machine learning. So that was the inspiration behind John and Yoram's algorithm, which is called AdaGrad, where what they were doing in Ada Delta, where they were trying to estimate a little bit of what is called curvature information, which tells you kind of how much should I trust a step in every direction. The Hessian isn't something mysterious. It's just saying like, look, if there's a really big, difference in this direction versus a really small one in this direction, I should probably step more in the directions I care about. That's roughly all that's going on. So you can simulate that by assuming H has some structure. Maybe it's diagonal. Diagonal is super cheap. That's what they were doing. You can do diagonal plus low rank. That's another thing. Or you can assume that it compresses well, which is kind of what people were doing in what's called sketching. And so yes, that all comes up. So those family of algorithms are still widely used. And in fact, they form the basis of what we do. In fact, Adam you can look at as kind of a combination. Adam is the most popular optimizer as a combination of those ideas with what's called momentum, which is another idea. They use Polyak momentum, but it doesn't matter. But yeah, so that is exactly right. So it does come up. I don't mean to say it doesn't come up, but the core Newton method is not widely used in machine learning. Excellent question. The ideas are important. I'm not telling you things that I don't think the ideas. So maybe that should be the baseline. If I'm telling you, I think you should know it. But yeah, it is used, but it's used a little bit more circuitously or indirectly. And we don't have a segment on optimization because I think it makes people's eyes bleed. Well, I'm super happy to talk about it. I worked on it for like a long, long time. Other questions? These are great, phenomenal questions. That's no indifferent? All right. Okay, so that's all I wanted to get through today because we're going to start to do something that's in a different segment next time. So we saw the differences between classification and regression. We learned about this principle for probabilistic interpretation, which is maximum likelihood. That principle is absolutely key and critical. That's the thing that's going to scale from one model to the next model. Next time, what we're going to see is how we extend that to what are called generalized linear models. They have much more complicated link functions, much more complicated stuff underneath the covers, but they cover like a huge fraction of machine learning. And it took a while to figure that out. We derived logistic regression, and then this will be used in the next lecture, and we saw Newton's method. And I think I accidentally cut off and threw away the multi-class stuff, so I will make sure to bring that back.